Good day, ladies and gentlemen. Right now, we're going to solve a problem involving heat transfer and the unit operation, evaporation. To start with, we have this problem. A feed of 4,535 kilogram per hour of a 2.8% salt solution at 11 Kelvin enters continuously a single effect evaporator and is being concentrated to 3%. The evaporation is at atmospheric pressure and the area of the evaporator is 69.7 square meters. Saturated steam at 383.2 Kelvin is supplied for heating. Since the solution is dilute, it can be assumed to have the same boiling point as water. The heat capacity of the feed can be taken as 4.10 kilojoules per kilogram Kelvin. Calculate the amounts of vapor and liquid product and the overall heat transfer coefficient U. So, as you can see, here's a single effect evaporator diagram, and a cold feed is being supplied right here. So the cold feed supplied has a mass flow rate of 4,535 kilogram per hour and has a concentration of 0.02. Stated that the specific heat is 4.10 kilojoules per kilogram Kelvin, and the feed has a temperature of 311 Kelvin. And on the other side, it was stated in the problem that steam was supplied for heating and that the entering temperature of the steam is 383.2 Kelvin. So, also right here, as you can see, the boiling temperature inside the evaporator is 100 degrees Celsius, and the evaporator has an area of 69.7 square meters. So what is required in the problem is the amount of vapor that is emitted and the amount of concentrated liquid produced. And it was also stated that the concentration of the product is 0.03 or 3%. So we need to find the amount of vapor, liquid produced, and lastly, the overall heat transfer coefficient U. For the solution, since the problem is a steady state process, we could write the overall material balance this way. The amount of feed supplied is equal to the amount of the liquid produced plus the vapor emitted. And for the solute balance, since there's no solute in the volume, we could write the equation as F, the feed, times the solute fraction is equal to the liquid times the solute fraction in the liquid. So substituting the givens that we have, we could solve for the liquid. So 4,545 times 0.02 is equal to the liquid times 0.03. So the mass flow rate of the liquid is 3,023 kilogram per hour. And we could use this in solving the mass flow rate of the vapor using the overall material balance. So using the overall material balance, we could subtract this 3,023 kilogram per hour to the feed, which is 4,545. And now we have a mass flow rate of the vapor, which is 1,512 kilogram per hour. So in solving the U, in solving the overall heat transfer coefficient, we need to use the heat balance equation. But before that, we need to find the enthalpies. And where could we find the enthalpies? We could find the enthalpies in the steam table, except for the enthalpy of the feed. But we are given with a heat capacity of 4.10 kilojoules per kilogram. And with this, we could solve for the enthalpy of the feed. So the enthalpy of the feed is equal to the heat capacity of 4.10 kilojoules per kilogram Kelvin times the entering temperature of the feed, which is 311 Kelvin, minus the boiling point inside the evaporator, which is 373.2. Sorry. Next is we need to find the latent heat of the steam, and we could find that in the steam table. So the latent heat of the steam is 2,230.2 kilojoules per kilogram, and the enthalpy of the of the vapor is 2,257.06 kilojoules per kilogram. So after having these enthalpies, we could now proceed to the heat balance equation. So the heat balance equation is written in the form uh, feed times the enthalpy of the feed plus the steam times its heat is equal to the liquid times the enthalpy of the liquid plus the vapor, the mass flow rate of the vapor times the enthalpy of the vapor. And we could equate the LHL to 0 since the datum is at 100 degrees Celsius. So, and there's no boiling point rise. So, the feed, which is 4,535 times the enthalpy of the feed, which is equal to this, for 4.10 times 311 minus 373.2, plus the S, which is the unknown, the mass flow rate of the steam, times the latent heat of the steam, which is 2,230.2, is equal to 0 plus 1,512, the mass flow rate of the vapor, times 2,257.06, its enthalpy. So with that, we can now solve for the steam, which is equal to 2,049 kilograms steam per hour. Since we already have S, we can now solve for the Q. I mean for the U. So Q, as we all know, is equal to U times the overall heat transfer coefficient times the area times the change of T. This change of T is equal to the temperature of the entering steam minus the temperature of the boiling point temperature inside the evaporator. So with that, we also know that the Q is also equal to S, which is the mass flow rate of the steam times its latent heat. So we could now equate these two formulas, since both are equal to Q. So 2049, the mass flow rate of the steam, which we solved earlier, times its latent heat. But we need to convert it into joules since the latent heat is in kilojoules. So we need to convert it to joules by multiplying it by 1000. And this mass flow rate, which is kilogram per hour, we need to convert it into seconds. So there's 1 second, there's 3,000 seconds there's 1 hour per 3,600 seconds. So 2049 times 2,230.2 times 10 to the power of 3 times 1 over 3,600 seconds is equal to the unknown, the overall heat transfer coefficient U, times the 69.7, which is the area of the evaporator, times the change of T, the temperature of the entering steam, which is 383.2 Kelvin, minus the boiling point temperature inside the evaporator, which is 373.2 or 100 degrees Celsius. So we could now solve the U. So the U is equal to the overall heat transfer coefficient is equal to 1,823 watts per meter squared Kelvin. So the final answers that we have for the amount of vapor and liquid product, we have 3,023 kilogram per hour for the liquid. Mass flow rate for the vapor is 1,512 kilogram per hour. And lastly, the overall mass transfer coefficient is 1,823 watts per meter squared Kelvin. I hope I explained the problem clearly and that you have learned something from this. So thank you and always keep safe.
A single effect evaporator is required to concentrate a solution from 10% solids to 30% solids at the rate of 250 kilograms of feed per hour. If the pressure in the evaporator is 77 kilopascal absolute, and if steam is available at 200 kPa gauge, calculate the quantity of steam required per hour and the area of heat transfer surface. If the overall heat transfer coefficient is 1700 joules per meter squared seconds, degrees Celsius. Assume that the temperature of the feed is 18 degrees Celsius and that the boiling point of the solution is under the pressure of 77 kilopascal absolute and 91 degrees Celsius. So assume also that the specific heat of the solution is the same as for water, that is 4.186 times 10 to the power of 3 joules per kilogram degree Celsius. And the latent heat of vaporation of the solution is the same as that for water under the same conditions. From the steam tables, the condensing temperature of steam at 200 kilopascal gauge, 300 kilopascal absolute is 134 degrees Celsius, and the latent heat is 2164 kilojoules per kilogram. And the condensing temperature at 77 kilopascal absolute is 91 degrees Celsius, and the latent heat is 2281 kilojoule per kilogram. From the mass balance, so in the feed, the solids is 25, the liquids 225, so a total of 250. And in the product, solids 25, liquids 58, so a total of 83. So the evaporation total is 167. Um, so heat balance. Heat available per kilogram of steam is equal to latent heat plus sensible heat in cooling to 91 degrees Celsius. So the latent heat is 2.164 times 10 to the power of 6 plus 4.186 times 10 to the power of 3 times the temperature change 134 minus 91. So a total of 2.34 times 10 to the power of 6 joules. So in the heat required by the solution is equal to latent heat plus sensible heat in heating from 18 degrees Celsius to 91 degrees Celsius. So 2281 times 10 to the power of 3 times 167 plus 250 times 4.186 times 10 to the power of 3 times the temperature change of 91 minus 18. So a total of 4.57 times 10 to the power of 8 kilogram joules per hour. So now heat from steam is equal to heat required by solution. Therefore, the quantity of steam required per hour is 195 kilogram per hour. So in the quantity of steam per kilogram of water evaporated, so 195 divided by 167, so a total of 1.17 kilogram of steam over kilogram of water. So in the heat transfer area, temperature of condensing steam is equal to 134 degrees Celsius. So and the temperature difference across the evaporator is equal to 134 minus 91 is equal to 43 degrees Celsius. So getting the heat transfer area, so 4.57 times 10 to the power of 8 over 3,600 is equal to 1,700, the heat transfer coefficient, times the area and times the temperature difference across the evaporator. So the area is 1.74 meters squared.